Hi everyone. In this video we are going to introduce Chapter 5, which is titled Integration, and the first section of Chapter 5 is 5.1, where we approximate areas under functions. And in order to introduce that topic, first we need to understand what is meant by sigma or summation notation. And what it is a way to shorten a sum of terms. So what I mean by that is if I want to add the first bunch of digits together, 1 plus 2 plus 3, I could keep writing them out, or I could throw a dot 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 in there, plus all the way up to 19, and then 20, right? If I want to write that out, it would take a while to write it out in its entirety. It doesn't take too long to write it out with the dot dot dots, but a more shorthand way to write that is with sigma notation. So that is exactly equivalent to writing this expression. That is a sigma, a Greek letter. We write underneath it I equals 1, above it 20, and then after it the letter I. Okay, so what does that mean? All right, that notation means everything I have written above it. It means we are going to, when I see this symbol, I'm going to say the word sum. We are going to sum from I equals 1 up to 20 the expression I. And so that means I start at the bottom of the index and write that bottom number down and basically substitute it into whatever that expression is. That doesn't have to be an I. It could be a 3i, it could be a I squared, it could be a 4i plus 2. It doesn't matter what that is, but I start at the bottom number and substitute in 1 plus 2 plus 3 plus 4, etc., until I get to the top number, plus 19, plus 20. So yes, I did just rewrite everything I have written above, but that's what this notation means. It's a way to compress everything that I have written out into one shorthand expression. Now we will look at an example where we're going to write this sigma notation and evaluate it for the first one. Okay, so part A says write in sigma notation and evaluate the sum of the terms 3 to the ith power for I equals 1, 2, 3, 4, 5. All right, so what we do there for part A is I'm going to start with my Greek letter sigma, that is the sum notation. I'm going to write underneath it I equals, now the first number is 1, and the last number is 5. So it's the sum from I equals 1 to 5 of 3 to the ith power. Okay, and usually we use an I. Sometimes you'll see K being the index for our sigma notation. The other letters can be used too, most commonly I and K. All right, so that's what it means. That's how we write it with a sigma notation. And then we're going to substitute and evaluate. So we start at the bottom number, 3 to the first power, and count up from there, 3 to the second power. And this is a summation. They are always plus signs between these terms. 3 to the third power, plus 3 to the fourth power, and I'm going to stop when I get to my top number, the top of the top index, 3 to the fifth power. So that's what that's how we write that out. If you do type that into your calculator, add it all together, you will get 363. All right, that's A. Part B, write the following in sigma notation. In order to do this one, we have to recognize the pattern. All right, and the pattern, if you don't see it immediately, if you want to pause the video actually and try to figure out what the pattern is, go for it and do that. But if you don't see it, the first term is 1 over 1 squared. The second term is 1 over 2 squared. And now hopefully you see what the pattern is. 1 over 3 squared. 1 over 4 squared is 16. 1 over 5 squared is 25. And so we can see that we start at 1 and go up to 5. So the way that we write this using our sigma notation is the sum from I equals 1 to 5, because that's the two numbers that I highlighted in red, and the expression that we're substituting into is 1 over I squared, 1 over I to the second power. There is a lot of information on this slide, so I would encourage you to read through OpenStax on these tables. But what these are different rules and properties for our sigma notation. Essentially, you can kind of view them as formulas. So if I'm taking the sum from I equals 1 to n of a constant, right? So for example, if I have the sum from I equals 1 to 5, I'll use that for these, of 2, right? There's no variable to plug in there, but I'm still adding 2 with each index, okay? So when I equals 1, the expression is 2. When I equals 2, the expression is 2. When I equals 3, the expression is 2. When I equals 4, the expression is 2. When I equals 5, the expression is 2. Okay, there's no I to plug into, but we still get each of those 2's for the 5 indices. That's the plural of index. Okay, and because we get 5 of them, the shorthand formula for that is n times c. In this case, 5 times 2. All right, so that's the first formula. The second, if I have a constant times some term, I can factor that constant out in front of my summation. If I have a sum of terms, I can break that up into 2 separate summations. Same deal for a difference, a subtraction. And then take a look at this last one. This last one says that if I have the sum from 1 to n of some expression, I can break that up into 2 separate summations, one going from 1 to m, and the other from m plus 1 to n. So you can take a sum and break it up in the middle somewhere if you need to, for some reason. The next table, as I scroll down, is just a couple more formulas for summations. If I'm going from I equals 1 to n, and my expression is I, then the formula for that is n times n plus 1 over 2. If I'm summing a bunch of terms that are I squared, then the formula for that, a little bit more complicated looking, but ultimately it's a formula that we can plug into, n times n plus 1 times 2n plus 1 over 6. And then summing a bunch of cubes, the sum from I equals 1 to n of I cubed is given by that expression. So it's a shorthand way. If I needed to sum the first 100 cubed terms, I could, instead of adding them all up individually, I could use this formula and save some time. And we'll see with this example how we can use some of those properties and rules. So for letter A, we're going to write the sigma notation and then evaluate. And it says the sum of the terms I minus 3 to the second power for I equals 1, 2, 3, 4, 5, 6, all the way up to 200. All right, so that would take a while to do by hand. But for part A, to write it in sigma notation, we start with I equals 1. We're going up to 200, and then we're adding I minus 3 squared. Okay, I don't want to do that out by hand. That would take a while. In order to use the formulas above, what we need to do is first expand out that algebra, 1 to 200, and we get I squared minus 6I plus 9, right? I minus 3 times I minus 3, the result is a trinomial. And then what we can do with that algebra, or with that summation, let me throw it into parentheses, is split it up and factor. Okay, so here's what I mean. We're going to just break off the first term, I squared, and then we're going to subtract 6 times I equals 1 to 200, just I there, and then we're going to add the sum from I equals 1. And sometimes my summations look a little funky. You know, how precisely you draw them is not a huge deal. 1 to 200 of 9. All right, there we go. So we've expanded this out. So you can see I just broke it up into 3 separate summations. And when I had the 6, I factored that out in front. So how do I now use the above formulas? Well, for the one on the right, if I'm adding a bunch of 9s together, right? So I'm starting on the right here, just for, because it's the easiest one to write down. I'm adding up a bunch of 9s, right? 9 plus 9 plus 9 plus 9 plus 9 from I equals 1 to 200. So that's 200 times 9. That was the first property at the top of this slide. All right. In the middle, minus 6 times, I'll throw parentheses here, the formula for this one, if I'm adding from 1 to 200 of just my I index, that was the second table, what was it? The sum of n integers is given by n times n plus 1 over 2. So in our case, 200 times 200 plus 1, all divided by 2. All right, and then the first one, the sum of the first 200 squared terms, that one is n times n plus 1 times 2n plus 1 over 6, right? If you have open stacks open, you can kind of look at this and the formula at the same time. So this would be 200 times 200 plus 1 times 2 times 200 plus 1. So I'm squeezing that in there. And that expression is all over 6. All right, so that looks messy. Oop, I lost a plus sign there. All right, that looks a little bit messy. All right, hopefully we get that. So we're using the formulas to essentially save time, save computation. Okay, it would take a long time to do this out by hand if I didn't have these formulas. But now I've got something that I can just throw in my calculator and have it spit out an answer. And the answer that it would spit out is actually, and I'm just going to give you the answer for this one rather than go through each individual calculation, but it is 2,567,900 is the answer there. All right, so that's what part A gives you. And then for part B, I'll leave it just at the tippy top. Part B is the sum of the terms I cubed minus I squared, and my indices are from 1 to 6. That looks like this. I equals 1 up to 6, and then my expression is I cubed minus I squared. So the first and the key step here is to split this up, 1 to 6 of I cubed minus the sum I equals 1 to 6 of I squared. Now here's one where it might be easier to just compute, to just expand out, plug in 1, plug in 2, plug in 3, 4, 5, 6, and you can do that and check to see if the formula works, and it does. And that way, you don't have to take my word for it. But when we plug in from 1 to 6 of I cubed, the cubed one looks like this. The top of the index, 6 squared times 6 plus 1 squared over 4 minus, for I squared, the formula is the top index 6 times 6 plus 1 times 2 times 6 plus 1. All of that is over 6. Okay, plug all of that into your calculator and it will spit out 350. Also, if you just write out all 6 terms, I cubed minus 1 cubed minus 1 squared, 2 cubed minus 2 squared, etc., add them together, you will also get 350. The purpose for introducing all of that notation, that sigma notation, was to lead to this. And this is where we will basically spend the rest of the course. And the other kind of side to calculus, the other, the purpose of calculus that we were introduced to in the first part of the course was taking derivatives and looking at slopes. And now the latter part of the course is approximating area, using calculus to approximate and ultimately compute area exactly. Okay, and this is that notation with sigma is the introduction to this topic. So if I wanted to approximate the area under this curve, so the area under f of x down to the x-axis, right? F of x is not flat. I have formulas for areas of circles, of triangles, of rectangles, of parallelograms. There's nothing for the formula for the area under a curvy thing. Well, there is using calculus, which is pretty awesome. All right. And so that's what we're going to do as we move through the latter part of this section and throughout much of chapter 5. So we'll define here what is called a partition. All right. So if I have a set of points with indices, I equals 0 through n. Okay, so we are partitioning, we are breaking the x-axis up into sub-intervals. okay? X naught to x1, x1 to x2, etc. Okay, so what that means is visually, because that definition is fairly abstract, right? So I start at A and I break A to B up into a bunch of subintervals, into n subintervals. So in the case of what I just drew, it's 1, 2, 3, 4, 5, 6, 7 subintervals. Okay, that is called a partition. Okay, so the formal definition you don't have to be super concerned with. Just understanding that the concept of what we're doing is breaking up the interval A to B into a bunch of subintervals. And the purpose for that is so that we can draw some rectangles. Look at that. So this first next definition is the left endpoint approximation. So here's what we're going to do. Here's how we're going to calculate the area under a curvy thing. We're going to approximate it with rectangles. Okay, so I can draw my rectangles underneath some function because, hey, I bet you know, maybe, hopefully, what the formula for a rectangle is, right? The area of a rectangle, base times height. Base times height, base times height, base times height. And if I divide my region up into equal intervals, the bases of each of these rectangles are the same. And in the formula that I've got above in this definition, the base of that area is represented by this delta x right there. It's the change in x, the distance that I'm moving on the x-axis for each of my little rectangles. And then the height of each rectangle, the height right there, is determined by the left endpoint for each rectangle where it is on the function. So the height of the rectangle is just a y coordinate, right? So if I plug a into my function, I get the height of that rectangle. If I plug a plus that little bit into the function, I get the height of that rectangle. If I plug in a plus that little bit more, I get the height of the third rectangle. And so the formula there, that's f of x naught times delta x, that's the area of the first rectangle. F of x1 delta x, etc. We're adding up all of these areas. And if I want adding up a bunch of terms, that's best, most easily written with summation notation. Okay, so that's called the left endpoint approximation. And it's L subscript n. N is the number of subintervals, the number of rectangles that we are using. Well, I don't have to use just left endpoints. I can also use right endpoints. So this last part of the slide is the exact same thing as I have above, except instead of drawing the rectangles so that the left endpoint it determines the height, right? The right endpoint determines the height. So that's the only difference here, and we'll look at both types of problems. And the difference between the two, if I zoom out so that we can see both graphs, the difference between the two, maybe you can tell, one of them estimates the area, and the other one overestimates the area. So they're both pretty good approximations. One gets a little under, one gets you a little over, and we'll talk about ways that we can improve the approximation. Okay, let's go through an example where we find the left and right endpoint approximation for the area under a curve. Our function in this case, is f of x is equal to x squared over 2. So it's a parabola, x squared divided by 2. And then the number of rectangles, you can feel free to count them, n is equal to 6. Okay, so we've got x squared over 2. We have 6 rectangles, and our interval is from 0 up to 3. The difference between A and B, A was drawn with left endpoints, B was drawn with right endpoints, determining the heights of the rectangles. Okay, so one important piece of information that we can do right off the bat is compute delta x. Our formula for delta x, the width of each of our rectangles, is b minus a over n. The difference between b and a, the width of the interval divided by the number of rectangles. So in our case, 3 minus 0 divided by 6, or simplified, 1/2. For part A, we are going to approximate the area using left endpoints and 6 subintervals. Okay, we can write that using sigma notation. It's the sum from I equals 1 to 6, and the area of each rectangle, the left endpoints looks like this, f of x subscript I minus 1, that's all in the subscript, times delta x. All right, so what that means is we're going to start at this endpoint and get the height of that rectangle, this endpoint, 1, 2, 3, that endpoint, that point, and that point. Not at 3, because that would be 7 rectangles, right? We only have 6 rectangles, so we don't end up substituting 3 into our function. All right, so let's go through this. Substituting in for my first rectangle, that endpoint is f of 0 times the width of the rectangle is a half, plus the second rectangle, I've moved over a half of a unit, f of 1/2 times a half. Remember, each of these is a base times height area of a rectangle, plus f of 1 times a half. That's my third rectangle. Okay, I'm circling, it's getting a little bit messy, right? The height of that rectangle is determined by the function value at 1. The fourth rectangle, maybe I'll just point at it, is right there. Now we're at 1.5, f of 1.5. I'll write it as a mixed number. No, I'm going to write it as a decimal. f of 1.5 times a half. That's 4 rectangles. F of 2 times a half. That's 5 rectangles. F of 2.5 times a half. All those times a halves represent the width of the rectangle, and all of the f ofs represent the height of each rectangle. All right, now when I would definitely go to my calculator for each of these next few pieces. F of 0, though, I can do that. The height of at 0, 0 squared over 2. Well, that's 0 times a half. When you plug in a half squared over 2, you get 0.125 times a half. Plug in 1 squared over 2 is 0.5 times 1/2. You substitute in 1.5. 1.5 squared over 2 is 1.125 times a half. Substitute in 2. 2 squared is 4 over 2. 2 times a half. Substitute in 2.5. That squared over 2 is 3.125 times 1/2. Okay, so this is definitely a calculator question. This is definitely a pay attention to the little details type of question, but it is just, quote unquote, just 6. 1, 2, 3, 4, 5, 6 rectangles, length times width, that we're adding together. Type all that into your calculator, and you get that the area is approximately 3.4375. 3.4375. And that is an underestimate for the area of the region. Underestimate, right? You can see how all of those rectangles are a little bit under. Okay, if we want our overestimate for part B, actually, I'll scroll back up. If we want our overestimate, the only difference, a lot of this work would be the same, and if you want to see it all written out in OpenStax, you absolutely can. But the only difference is, well, we don't substitute in 0, right? This is the first right endpoint. So 1, let me actually write these down. This is 1, 2, 3, 4, 5, 6. So we don't have a rectangle at 0, so we lose this first term here. And we do have a rectangle at 3, so we gain an additional term at the end of the expression. So L sub 6 and R sub 6 are really, really similar. They just kind of differ by which endpoint they include. Okay, and I'll put the answer to part B over here. Part B is our R sub 6. The area is approximately R with a subscript of 6, which is equal to 5.6875. And you can try that out yourself. Just get that last term added on, and it should work out without too much difficulty. But that's our over approximation for the area of the region. Okay, so now that we've shown that we can approximate area, we can under approximate or over approximate area using rectangles, area under a curve using rectangles, the question becomes, how do we improve that approximation? All right, and so for that, I will show you this example. In this one, our function f of x is equal to the quantity x minus 1 to the third power plus 4. That's what the function that we're looking at is, and our interval is from 0 to 2, and in this we can clearly see that the number of rectangles is 4. Okay, the delta x, the width of each rectangle, would be delta x is 2 minus 0 divided by 4, which is a half. That's a common width for your rectangle that you'll see come up often. All right, and if we wanted to do L subscript 4, the leftmost rectangle is f of 0 times a half plus f of 0.5 times a half plus f of 1 times a half plus f of 1.5 times a half. All right, and there we would have our 4 rectangles. Substitute into our function, f of 0, f of 0.5, f of 1, etc. Multiply them all by a half, add it together, and you get that L4 is 7.75. Now, I know I did that a little bit more quickly than the last example, but that's because we're building to the next piece. The question is, how do I do a better job of approximating that area? And the answer is, well, draw more rectangles. So, as I scroll down here, if we this is the same function, by the way. The pictures look a little bit different. I couldn't make them look the exact same, okay? But the one on the left, if I look at the same function, but instead of just 4 rectangles between 0 and 2, now we're going to say, all right, I'm going to I'm going to draw 8 rectangles between 0 and 2. If I have 8 rectangles, my delta x is now 2 minus 0 over 8, or 1/4. So each rectangle now has a width of 1/4, and I move over a quarter as I move through the interval when I substitute into the function. Okay, so that's going to have its own area that looks closer, right? I'm not missing quite as much as I am when I have all of those rectangles. And then if I want to make the approximation even better, heck, if I can do 8 rectangles, why not do 32? That would take a terribly long time by hand, but look how close 32 rectangles gets me to the actual area underneath that curve. And if we look at the answers that we get here, right, with 4 rectangles, we saw above we got an answer of 7.5. With 8 rectangles, 7.75. With 32 rectangles, 7.94. And we also have the area using the right endpoints. Okay, so it looks like from above, we're getting a little closer to 8. From below, excuse me, from the left endpoints, we're getting kind of close to 8. From the right endpoints also, it looks like we're getting closer to 8. Gosh, if only there were some way to just keep adding more rectangles, you know, like an infinite number of rectangles would make the exact perfect precise area under that curve. Do we remember how to make, you know, something go to infinity? Well, that's called a limit, right? The last piece to this rather lengthy section does kind of bring it all together in an awesome way in forming Riemann. That's how you say this word, Riemann Sums. Riemann was a mathematician that basically developed this process. Bernard Riemann, he did math in the 19th century and got this named after him because he's developed this process. Okay, so we have a function on some interval. P is a partition. We've broken it up into subintervals. Delta x is the width, all right? And then this xi star is any point inside of that interval. We've been talking about left endpoints, right endpoints. Technically, this xi can be any point inside of the xi star can be any point inside of the interval, but for our purposes, we've been using left or right. Our Riemann sum is the sum from I equals 1 to n. f of xi star delta x. We're just formalizing what we did in the previous few examples, right, where I add up a bunch of rectangles, length times width. All right, but then the part where it becomes awesome is we can compute the exact area under the curve by drawing an infinite number of rectangles, which sounds complicated. It would take a while to do it. We don't actually draw them. We take a limit as n approaches infinity. So we let this upper index approach infinity, and then we essentially have an infinite number of rectangles that we're adding together. And that will give us the exact area underneath the curve. We're not going to go through an example using the limit for a Riemann sum, but just introducing that topic is kind of how we close out this section. All right, that is the end of this video. Try some homework problems. Please let me know if you run into issues. Thank you very much for listening. Have a wonderful day.